let's talk about radioactivity. Radioactivity is a tremendous part of physics, and it is just an awful lot of fun. Okay? The quote I really like is when they broke up in molecules, they found they were stuffed with atoms. But when they broke up in atoms, they found they were stuffed with explosions. So you can take any molecule and break it up, you're just going to get atoms. But when you smack open an atom, you're going to get an explosion. Now, these are three prominent scientists in the study of radioactivity. Becquerel was one of the founding fathers. He discovered the spontaneity of radioactivity. Basically, radioactivity happens without you necessarily doing anything. That's what it means by spontaneous. You don't have to necessarily incite it. While Pierre and Marie Curie were two scientists who worked with him. They were married. Madame Curie is one of my absolute idols. There's a wonderful story of how she forgot something in her lab, and she went back, and it was late, and she looked over, and she saw this beautiful blue glow coming out of the test tube of thorium she had been using. There is a picture of her hand that she used to hold this test tube up and look at it in the light, and of course she got cancer. Now, let's do a little bit of notation. Don't panic too much about this. We're not going to beat this too horribly. You did this in chemistry. If I give you an element, and just for example's sake, let's use U, the top number is the mass number. This is the number of protons plus the number of neutrons, while the bottom number is your atomic number, and this is just the number of protons. All right? So this is protons plus neutrons. This one will always be bigger. The top number is always going to be bigger than the bottom number. Now, isotopes are the same element, but they have different masses. All right? Why do they have different masses? Well, they have to have the same number of protons. It is because of the number of neutrons. Isotopes have different numbers of neutrons. The neutrons are neutral. Now, radioactivity occurs when, for some reason, the nucleus is unstable and it releases energy. So we're always going to get another particle and some sort of energy. That's the whole point behind radioactivity. So suppose we have something unstable and we have spontaneous decay. We're going to get one of the following particles. We're going to get an alpha particle, which is a helium nucleus. We're going to get a gamma ray, which is just kind of deadly energy. You could get protons. You can get beta particles, beta positives and beta negatives, and then you can get neutrons out. 4 types of radioactivity I need you to know are alpha. It is an ejected helium, and this is why we write it. A beta is an ejected electron, and this is the way we write it, 0, -1. A positron is an ejected anti-beta, while gamma is just energy. We're going to discuss these in a bit. We can also get a proton or a neutron. Now, alpha decay. Why do we use alpha decay? Well, you use them in smoke detectors. All right? Basically, the alpha particles ionize the air between the small gap, and then there's a little current going through. When there's smoke particles, it breaks that current, and you get an alarm. So you have radioactivity in your home. Beta decay, there's not a lot we can do with this besides beta voltics. We also, it helped discover the neutrino. Now, positron, the beta plus decay we use in PET scans, the positron emission tomography, which is used in nuclear medicine all the time. It produces beautiful 3D images of the body. It helps a lot in medicine. Now, gamma decay is really fascinating. It's very dangerous. It is just dangerous. It's used to sterilize things, and it's also used by Homeland Security. If you look at this, basically, they have shot gamma rays, and you see the stowaways here and here hiding. Now, they're shot with this for very, very short periods of time. They don't get, hopefully, sick and die from it. Now, let's talk about half-life. If I start with some amount and I watch radioactivity, it's going to decay in this curve that looks like this right here. Now don't worry, we're not getting into all the exponentials. Basically, half-life is how long does it take for one half of the material to go away. So this is a half-life, and we're going to call that T subscript 1/2. And without worrying about the formula to get here, it's 0.693 divided by lambda, where this is the decay constant. Clearly, the larger the decay constant, the shorter the half-life. Let's talk about the different types of energy release. One is fusion. Fusion, think about it, it's when you fuse two things together. It's when you take like charged atomic nuclei and push them together that results in the release or absorption of energy. So fusion occurs in the sun. Whenever you say sun, think fusion, because that's what we're talking about. Also, IFE power plants use fusion. Fission is when you break them apart. When you have a chain reaction, free neutrons get released and cause more events. So basically, let's see if we can have a chain reaction. Here, I have my atoms, and say this one breaks apart for some reason. It shoots out, and the energy hits this one and breaks this one apart. This one shoots out, breaks this one apart, and so on and so on. This is what a chain reaction is. You can see these can get out of hand very quickly. So fission is when you break apart. Fusion, when you push together. Now the differences in fusion and fission, please study the chart. Fission is not normal, it is not natural, while fusion occurs in stars like the sun. Fission can occur, but it's not normal. Fission has many highly radioactive particles, but fusion gives fewer particles. The energy released by fission is 1,000,000 times greater than a chemical reaction, but it is less than fission. Fission gives 3 to 4 times greater, fusion gives 3 to 4 times greater energy than fission. So we would have chemical, then fission, then fusion. Nuclear weapons, there is a fission bomb. We also call it the atomic or atom bomb. There's there's a fusion bomb that's a hydrogen bomb. Know the definition. Fission is the splitting of large atoms into one or more smaller atoms, while fusion is the fusing of two or more light into a large one. Know the conditions. Fission occurs when you have a critical mass of the substance and high-speed neutrons are needed, while fusion occurs when you have high density, high temperatures. High temperatures, think sun. And the energy requirements, it takes very little energy to split two atoms. However, it takes a lot of energy to bring two or more protons close enough to force them to overcome the repulsion. So,